So let's get started. Let's talk about overclocking. It's the practice of increasing the clock rate to make your computer go faster. And it's quite common. It's been around for years when you had to do it in the BIOS. There are even competitions that happen yearly to try and overclock a machine. Because one of the problems of overclocking is that your machine will get hot. So you either use liquid nitrogen or you have a very large heat sink. And there are an awful lot of applications out there right now that enable you to change the frequency on your machine. There's throttle stop, RM clock, CPU-Z, AMD overdrive, CPU tweaker, and they're just a few that I found with a very quick search. Now, how do they work? They use something called DVFS, dynamic voltage and frequency scaling. And all that really means is changing the voltage and frequency dynamically. It's almost like the clue is in the name. Why would you want to do that? Well, there may be occasions when you want your computer to work differently. If you're playing a game, you want a fast response. If you're going to put it in a hospital, you don't want it to crash. And if you're putting it in the cloud, your costs need to be low. And historically, you did this in the BIOS, or you pressed a button. I don't know if anyone's old enough to remember that turbo button that you had to press that basically made all games unplayable. Well, CPU manufacturers have changed things and made it easier. And the way they've done that, they've enabled memory-mapped registers. Really simply, this means changing your software to write something to a register which changes your hardware. And this led to my favorite attack, if you can have a favorite attack. It's called clockscrew. And that's exactly what they did. They used these memory-mapped registers, and they created a new class of fault attacks. Because when I say fault attack, this is what you think of. Everybody has to get an oscilloscope out to create a fault attack. But these guys went, okay, if we can do it through software, maybe we can have an attack that doesn't require me to use an oscilloscope. So this is their attack. Within software, they modified the registers to change the frequency, and by slowly changing the frequency, they produced errors in calculations. Now, you might be thinking, and you would be right to think this, don't you have to be root to do this? Yes. So if you're root, why not just shut down the computer? What advantage is there to this? Well, they were specifically looking at ARM. And ARM has something called trust zone, and it's an enclave. And what they discovered was that when you change the frequency and voltage, you're doing it for both trust zone and normal code. So if you can fault something in normal code, you can fault it in this enclave. And they used a Nexus 6, and they were able to get an AES key out of the enclave, and they were also able to trick trust zone into signing self-signed apps. Okay, this was on ARM. What about Intel? And this is where we come in. First question, can we do this on Intel? Can we modify something? And we decided to go after voltage, not frequency. First thing is, are there memory mapped registers? This is where you say thank you very much to the internet, because you do a Google search and you discover, yes, model-specific register, hex 150, magic. It is not documented by Intel at all. They don't want you to know about this. But that's okay, because we have the internet, and someone on the internet worked out how it works. So you have a plain ID. That bit is just saying, what is it that you want to change? And in this case, we're just changing the core. You also have to change the cache, which actually share the same voltage plane. And the offset just says, am I going up or down, and then by how much? So let's use it. Let's see if we can do this and undervolt our Intel machine. First thing I did is I just ran a test to find out what the base voltage was when the machine's doing nothing. Then I decided to undervolt, and this is how you undervolt. It's first thing I wanted to do was to set my frequency. That's actually not very hard, because there's a nice little app called CPU Power that will do it for you. You say, make my maximum frequency 1 gigahertz. Make my minimum frequency 1 gigahertz. My computer is now running at a frequency of 1 gigahertz, yes, that's magic. And how do we change it? Well, again, thank you to the people on the internet. I'm going to put the model-specific register into the kernel. That's something you do have to do. And let's just look at the code to do it. It's not very complicated. There is one line of code there that is going to open that model-specific register. Let me know when you spot it. Yep. That's it. That's the one line that you need. Then obviously you're going to have to write to it. And again, somebody on the internet had done me the calculation that you need to do. So all I'm saying is minus 250, and there it is, it's doing it. So I thought, let's crash the machine. That's what we decided we'd do. Let's undervolt and see if we can crash it. And that's what we got. So we now know idle, and we now know where we can crash it. So the question is, what happens in between those two spaces? Is there anything we can do there? Specifically, can we fault it? And how are we going to test this? So I wrote a really, really simple bit of code. I will let you look at that and digest the complexity of that for a second. Can we ever get here? No. I mean, the answer to that is quite clearly no. You should never get there. 21 is always going to equal 21. Obviously, I'm a elite hacker, so I didn't use the numbers 7 and 3. I used dead beef and 1, 1, 2, 2, 3, 4, 4. Can we ever get here? The very last line at the bottom is just saying, if we do ever get there, I want to flip the wrong result with the right result to see what's changed. So let's have a look. Not playing. So what I'm doing here is I'm going to multiply dead beef by 11222, and I'm going to slowly undervolt, and we're just going to see what happens. Nothing at minus 254, nothing at 255, nothing at 256, 257. We've got a bit flip. We've got a result, and we've got a bit flip, and you can see that from the XOR. It's only a single bit, so I'm going to run this a few more times because I want to know if it's only ever going to be that one bit flip. Now what I'm doing is I'm just randomly generating numbers because I want to see if it's just one bit flip or if it's going to be lots of different ones. So again, it's just randomly generating numbers. Another bit flip. Oh, it's the same bit flip. Maybe the only fault I'm ever going to get is this single bit flip. So I'm trying a few now. I got a different bit flip. And again, a different bit flip. So I'm bit flipping. Great. You'll notice the bit flips, when they do flip, when we undervolt, they're always contiguous. They're always next to one another. So there's my idle, there's my errors, and there's my crash. And actually, the areas in the middle were where we found we could do it the most consistently without the machine crashing, which was lovely. Yes. Yeah, okay, so someone on the internet doesn't like our attack because, hey, you've got to be root. But as we spoke about the ARM thing, it's the same thing. Let's meet SGX. And this is where it becomes interesting, and this is why this is a possible attack. SGX Software Guard extension, it was 5 years ago, it was introduced as an extension to the x86 instruction set, and the idea is to protect an application, to make sure it's protected even if you're root and you're on the same machine as me. And this is how it works. You create an enclave, and when you do that, it creates a little trusted bit of memory, and that bit is encrypted. You can't read it unless you have the key, which I have got because I've created the enclave. You call it, you have to go through a call gate, so you have to define how you can call this trusted function. It runs, again, in encrypted memory, returns, and the operating system cannot access it. In physical memory, there's a little space, and it's called the enclave page cache. And this is encrypted. And it means that you can't take the memory out and put it into another computer because it uses the memory encryption engine on your machine. So what we're going to look at now is me trying to do the same thing. We're going to try, on the right-hand side, you are looking at user space. So I'm undervolting in user space, but on the left-hand side, I'm doing these multiplications, but inside SGX. Theoretically, I'm sort of expecting that I'm going to get an integrity check. Because if I do get a bit flip, it should tell me, and it should say that's not right. And at the bottom, I'm sorry, this is right at the bottom of the screen, I'm getting a bit flip, and it's the same bit flip that I'm getting in user space. And that's really interesting, because it means whatever tests I'm doing, there's the user space one, whatever tests I do in user space will have an effect on SGX. We can bypass the SGX integrity checks. And for those of you who know Rowhammer, it can't. So let's go back. This is why I love the internet so much. This guy has posted this at 1:59 a.m. on December the 11th. I think it's 8 minutes later, somebody else replies, so I don't have to, going, 8 minutes. To which the original guy actually replied with, oh, sorry, thanks. What? That doesn't happen. So we just created lots and lots of random numbers, and we just started to see if it's the same bet flip again and again and again. And guess what? It is. We've got something that we can repeat. And let's have a look at some of these and the way it works. The smallest number we got that we could fault was this. The smallest second number we could fault was 1. And the smallest result was this. This is an interesting thing, and I'd love to know if you have an answer to why this is. We can fault this multiplication. We can't fault this multiplication. Don't know why. If you have any ideas, come and tell me. Oh, yeah, I did. I promised that we would plunder. We'd steal some stuff from SGX. So let's look at RSA. I know nothing about crypto, so this is going to be quick. But let's try and plunder. Let's try and plunder from RSA. Many RSA implementations use the Chinese remainder theorem, and they can be attacked. So we're going to try and attack it. We're going to wait for the first fault. So that trigger fault bit is that multiplication we saw. We're going to wait for a multiplication fault. Then we're going to do a decryption. Can we get a fault? Let's have a look. So I'm trying minus 239, and right at the bottom it's saying all fine. All fine. OK, maybe minus 239 isn't going to work, so minus 240. We got an RSA error. That means that big load of text is an incorrect decryption. And again, thank you to the people on the internet for providing me with the Lenstra attack for RSA in a Python script. So all I had to do was pump in the output, and I got this. I got this thing at the bottom, this Lenstra attack. I don't know what it is, because like I said, I don't know crypto, but I do know how to Google. So let's just have a look at the source code and see what I found, because I found something. I found P. Now, even with my Googling skills, P is part of the private key. If you've got P and you know N, you can find Q, and that you can find D, and then you can actually decrypt. So to summarize, we have just got out of SGX, which is an encrypted thing that is protected with integrity checks, we've just got a key out. We've just done some plundering. And I promised you pillaging. Well, so Intel have this new set of instructions that is the AES instruction set. So I'm going to try and pillage this. AES can be attacked if you can get a fault in the 8th round. So I'm going to do this one slightly differently. Instead of waiting, I'm just going to do 2 encryptions and compare them. Again, this should never exit. So let's undervolt. Remember, it has to be in the 8th round. If it's not, I can't use it. That's in the 4th. That's not going to be any good. 5th, not any good. 5th, not any good. And this is genuinely, I did genuinely run this. So, 8th. So we've now found a faulty ciphertext that we can use. I actually ran it twice, just for ease of the presentation. And again, thank you to someone on the internet for writing a differential fault attack that I used. I used the first pair, and then I used the second pair, and the first pair came up with 465 possible keys. The second one came up with 200 possible keys. So theoretically, I should be able to overlap them, and only one key should overlap. And there it is. I've now found another key. I've plundered and I've pillaged. And there's to prove that really is the key. There's the key in source control. Right, hold tight. We're going in, guys. The water's going to get choppy. There's one more thing that we can do. That was crypto, but it doesn't just have to be crypto. There's a nice line of C. Why am I interested in that line of C? It's pointer arithmetic. I'm just taking an offset, finding the address of that offset, and putting it into a pointer. Well, the reason that's interesting is this is what the compiler will turn it into. Hex 24 will be the size of the structure, but there's a multiplication. And we know that we can fault multiplications. So this is a little hard to understand, but I think it makes sense. I've started the enclave in debug mode, so I can see the size of it. I can see the top and the bottom of the memory. If I can write outside of that, either above or below, I'm writing in user memory. So all I'm going to do now is I'm going to repeatedly run that one single line, that pointer arithmetic. I'm just going to write to the pointer, write to the pointer, write to the pointer, I got a fault. And that address is actually in user memory. It's not in the enclave. And that means it's not encrypted. So anything that should not be encrypted, anything that should be encrypted has now been written. And let's just find in the page fault what it actually was. It was dead beef. And this is one of those moments where I kind of wish I'd thought about ending this before I started the recording. That does say dead beef, but obviously the endianness has switched it. So again, to summarize, this one's kind of mind-blowing because it's not crypto. It's just code that doesn't have a bug in it. Somehow we've faulted just normal code by using pointer arithmetic, knowing what the compiler's going to do. So, to summarize what Plundervolt does, it's a new type of attack against Intel chips. It breaks the integrity of SGX. And within SGX, we've found an AES key. We've found an RSA key. We've induced memory corruptions in code that doesn't have any bugs in it. Pew, mind-blowing. And we've made the enclave write some secrets to untrusted memory. I'm going to show you something that just made me laugh. I discovered that if I'm logged on, so this is me logged on over here at minus 240 volts, and my supervisor rang me and said, I can't log on to the machine. And every time I'm using SSH, I'm getting an error. And this is him trying to log on as I was undervolting. He's just trying to SSH connect into it. It's a bit of trolling. Weirdly, you can stop somebody else logging in, presumably because there's multiplications or crypto or something happening there. And the minute I decide to stop undervolting, my supervisor was able to log in. Set it to 0. Hey presto, he's logged in. He wasn't very impressed that I had been deliberately doing that. That is my talk. We've done that. There we go. That is my talk. This is the paper that it's based on. You've already seen Daniel and Yo earlier. They're very clever people, and we had to have a logo, obviously. And thank you to all these people, and these are the acknowledgements. Thank you very much.
Good. Room for questions?
Is it known which code actually executes inside the SGX? Is it open source or?
Intel's SGX isn't. No, it's not open source.
So no one knows what is running there, yes?
You write your own code, so you write the enclave. Is that what you mean?
Yes.
So does someone want to answer that for me?
Well, the last time I looked at that specification, then you had to sign the code, and basically it wouldn't run unsigned code.
Yes, we're talking about code that has been signed that is running inside SGX. I think what you're talking about is a potentially really interesting attack, which is can we get the key out? And that's something we didn't have enough time to try and do.
So you have the code, yes or not?
Yes, it's our code that we wrote for the SGX.
My question is regarding the different CPUs. You mentioned ARM, Intel. What about AMD? And also then, is this a new class of vulnerabilities that will be mitigated similarly as was the case for smart cards? Because for the smart cards, fault induction is long-term thing, and you can still do this, but it's pretty hard at the moment.
So a couple of things there. I know people are working on AMD at the moment. It's not out there as much as ARM and Intel, so I guess it's less interesting as a research project. And the other thing you said, the mitigation. So Intel have just basically turned off MSR hex 150 if you're running SGX. So you have a choice. You can either overclock your machine or you can run SGX. You can't do both. That's the way they've mitigated it for now. I'll be interested to see what they do with future.
For the smart cards, the mitigation is so that they are like trying to detect the fact that voltage actually dropped, and they are then...
It's really hard. Actually, Daniel and Yo, who are here, will know because they wrote the chapters on the mitigation. Actually, mitigating this on a laptop is really hard. How are you going to know? Do you stop someone changing the voltage when you go into SGX? How do you know when it's dropped? Are you going to add something extra onto your voltage to start sort of measuring what the voltage is? I'd imagine that's quite a...
You can't prevent, but you can, for example, double run the algorithms to prevent CRT to output the data that are buggy.
I mean, talk to Intel. They probably would like to hear how to fix it, because at the moment they've just turned it off.
Have you looked at other devices on the system, for example, TPM or other things attached to the bus but not necessarily the CPU?
No. Okay.
Have you done any experimentation to see if other memory encryption technologies like MKTME or SME are vulnerable to this sort of attack?
We didn't. We stopped at this point because we had a paper to write. So we had enough, so we wrote the paper, and then obviously now we're in the situation where Intel have disabled it. So there were other things that we were faulting, we just couldn't get full attacks out of them. So elliptic curve we were getting faults on, but we weren't quite sure in the time frame we had how to turn that into an attack. So we are getting faults in lots of different things. Turning them into an attack was the hard bit, obviously.
Any more questions? If not, let's thank the speaker.
Thank you.